Hi, this is the second video of a playlist about the preparation of alkenes. In this video, we'll have a look at the dehydration of alcohols. This is an important reaction because alcohols are readily accessible by reduction of acids, esters or ketones, and many C-C bond-forming reactions also yield alcohols directly. Some alcohols can be dehydrated just by heating with acids or bases, but often some kind of derivatization will enable elimination under milder conditions. You can find a more detailed discussion of elimination mechanisms in part 1 of this playlist. Hydroxide is not a good leaving group, but it becomes one by protonation. Ethers and rearranged products are common byproducts of acid-catalyzed dehydrations. To suppress the formation of these byproducts, hydroxy groups are often converted into better leaving groups, for instance by esterification or sulfonylation. The elimination of sulfonates and halides is discussed in the first video of this playlist. Simple primary alkanols do not undergo dehydration easily and usually require some activation. Alcohols with electron-withdrawing groups or arenes in position 2 or benzylic alcohols, however, can often be dehydrated directly without activation. More resistant are 2-alkoxy alkanols or alcohols with electron-withdrawing groups in position 1. Pyrolysis of 6-chlorohexanol at 700 degrees Celsius, for instance, yielded mostly hexanol without elimination of water. Elimination of acetic acid from the acetate, however, already occurred at around 600 degrees Celsius and was faster than the elimination of hydrogen chloride. Secondary alcohols are easier to dehydrate than primary alcohols. Here, a substituted cyclohexanol was heated with triphenyl phosphate, the weak base quinoline, and NMP to 204 degrees Celsius for 3 days. A mixture of the expected cyclohexene and 3% of an isomer was obtained. The acid-catalyzed dehydration of simple primary alcohols is difficult and requires harsh conditions. In this optimized procedure, dodecanol was dehydrated by strong heating with 1% of aqueous triflic acid. The main product was the terminal alkene and only a small amount of ether was formed. Alcohols with electron-withdrawing groups in beta position are easy to dehydrate. Aliphatic aldehydes, for instance, often yield aldol condensation products during storage at room temperature. In this example, crotonaldehyde was converted into a chlorohydrine by chlorination in water. Upon heating, acid-catalyzed dehydration occurred. Styrenes readily polymerize upon concentration, and the preparation requires some precautionary measures. Here, a phenol was added as a radical trap. The dehydration was accomplished by heating with 10% of potassium bisulfate and distilling the product off from the reaction mixture. Tertiary alcohols are still more easy to dehydrate than secondary alcohols. In this case, however, the product readily rearranged with acids. If the starting alcohol was treated with boron trifluoride etherate at -78 degrees Celsius for only 2 minutes, the main product was the Hofmann exocyclic olefin. This compound isomerized to a mixture of internal alkenes within 20 minutes at -78 degrees Celsius. At 0 degrees Celsius, only a completely rearranged product resulted. Other acids gave a similar result. The rearranged product was formed by hydride migration to the initially formed tertiary carbocation, followed by stereoselective Wagner-Meerwein rearrangement and deprotonation. Some carbohydrates can be dehydrated in high yield just by heating with an acid. In this example, fructose was dehydrated to hydroxymethylfurfural with an acidic ion exchange resin. Most carbohydrates, though, will just oligomerize when heated with acids. Aldol condensations often require careful optimization to maximize the yield. The initially formed alcohols can fragment into the starting materials, and the final product may undergo Michael addition or further aldol condensations. In this example, the first aldol addition product of acetone was dehydrated with phosphoric acid. Also, heating with elemental iodine can bring about this dehydration, as shown in the second equation. This here is another old example of iodine-catalyzed dehydration. I suppose that iodine first acted as Lewis acid and after reaction with water to hydrogen iodide and iodic acid as Brønsted acid. Acetic acid is manufactured industrially by carbonylation of methanol in the presence of catalytic iodide and rhodium. In the absence of carbon monoxide, this catalytic system can be used to dehydrate primary aliphatic alcohols, as shown here. The conditions were relatively mild, but ethers and isomeric alkenes were also formed. Alcohols with arenes or electron-withdrawing groups in position 2 can sometimes be dehydrated under alkaline conditions. In these two examples, elimination of water occurred upon treatment with potassium hydroxide. If you are trying to purify the starting alcohols, partial dehydration may even occur during distillation and may be difficult to suppress. I'll show you now some practical activation strategies to convert alcohols into alkenes in a one-pot reaction. Even with the most reactive of these reagents, primary alcohols will not yield alkenes but other products. In this specific instance, thionyl chloride gave a large amount of alkyl chloride as byproduct, but its formation can be suppressed by optimizing the reaction conditions. Otherwise, phosphorus oxychloride or triphosgene in the presence of weak bases can also be used to dehydrate tertiary alcohols. With primary alcohols, however, these reagents will mostly yield alkyl chlorides or other derivatives. In this example, a tertiary acceptor-substituted alcohol was dehydrated with thionyl chloride in pyridine. The olefin was formed with high regioselectivity and an acceptable yield, while the phenolic hydroxy group remained unchanged after aqueous workup. The starting alcohol of this example was highly reactive, being both allylic and benzylic with an electron-rich arene. Thus, dehydration with a slight excess of phosphorus oxychloride proceeded under mild conditions and yielded mostly one isomer of a conjugated diene. Here, the starting alcohol was much less reactive than that of the previous example. Still, treatment with an excess of phosphorus oxychloride in pyridine at room temperature gave a high yield of alkene. In this example, a tertiary alcohol containing a terminal epoxide was dehydrated with triphosgene. A mixture of two isomeric alkenes resulted, but the epoxide underwent complete conversion into a dichloride. This is again a dehydration of the tertiary alcohol shown earlier that rearranged under acidic conditions. One diastereomer of this alcohol could be cleanly dehydrated with methane sulfonyl chloride and dimethylpyridine to the exocyclic alkene. The other diastereomer was less reactive and only yielded a mixture of internal olefins. In this example, the starting alcohol was easy to dehydrate because of the acidifying effect of the nitro group. Phthalic anhydride was used as a non-volatile dehydrating agent, and the alkene was distilled off directly from the reaction mixture. Here, a fourfold substituted ethylene was prepared with high stereoselectivity by dehydration with Bock anhydride. Tertiary alcohols do not react readily with acylating or carboxylating reagents, and a strong base was required to bring about stoichiometric deprotonation of the alcohol. The mixed terts-butyl carbonate was formed at 15 degrees Celsius and heating to 130 degrees Celsius for 24 hours then yielded the target alkene. Mixtures of triphenylphosphine with halogens convert most alcohols into alkyl halides under mild conditions. In the case of tertiary alcohols, however, elimination can occur, as in this example. The primary hydroxy group, however, was only converted into an iodide. In the second example, first a reactive allylic iodide was formed, which then underwent a second elimination, yielding a conjugated diene. And in the third example, an enol was formed, which tautomerized to a ketone. The product of the reaction of methyl iodide with triphenylphosphide has a similar reactivity toward alcohols as mixtures of triphenylphosphine with iodine. This reagent also converts alcohols into iodides, but can also cause dehydration under certain conditions. Here 4-methylcyclohexanol was dehydrated by heating with this reagent in the polar aprotic solvent DMI. If both terminal and internal alkenes can be formed, dehydration by intermediate formation of an iodide mostly yields the thermodynamically more stable, more highly substituted internal olefin. This is a rare example of enantioselective dehydration of a racemic alcohol. One of the enantiomers underwent dehydration faster than the other one, what enabled a kinetic resolution of the starting alcohol. There are two sophisticated reagents which can be used to dehydrate secondary or tertiary alcohols, sometimes with high regio or stereoselectivity. These are the Burgess and Martin's reagents. Both are expensive and generate a lot of waste and should only be considered if all other options fail. Burgess reagent is prepared from chlorosulfonyl isocyanate as shown here. It is a water-sensitive sulfonylating reagent that reacts with alcohols first by displacement of triethylamine. Primary alcohols unfortunately cannot be dehydrated with the Burgess reagent and are only converted into carbamates as shown here. Martin's reagent is prepared by oxidizing diphenyl sulfide with bromine in the presence of a fluorinated tertiary alcohol. Upon reaction with primary alcohols, no alkenes but only ethers are formed, as in this example. In this example, a tertiary alcohol was dehydrated both with the Burgess and Martin's reagent. The Burgess reagent yielded the Hofmann product with higher selectivity than Martin's reagent. Here, Martin's reagent was more selective than the Burgess reagent. With phosphorus oxychloride, however, a high yield and regioselectivity could also be achieved. Thus, it always makes sense to first try thionyl chloride or phosphorus oxychloride in combination with various bases. Like 1,2-dihalides, it is also possible to reduce 1,2-diols to olefins. This can be achieved with molybdenum, rhenium or vanadium complexes. Alternatively, diols can first be converted into cyclic thiocarbonates, carbonates or acetals. Pyrolysis or treatment with some activating reagent can convert these cyclic derivatives into stabilized carbenes, which then fragment into olefins and carbon dioxide. In this example, a diol was reduced to a terminal alkene with another secondary alcohol and 1% of rhenium carbonyl. Despite the high reaction temperature, almost no byproducts or isomers were formed. Also, acceptor-substituted alkenes can be prepared this way. Here, diethyl fumarate was obtained in high yield from diethyl tartrate by heating with zinc and 10% of ammonium perrhenate. Much higher temperatures are often required to generate carbenes by alpha elimination. Here, a glycerol-derived cyclic orthoester was heated and distilled with an acidic catalyst at 270 degrees Celsius. An acceptable yield of allyl alcohol resulted. A less expensive route is the reduction of glycerol with formic acid, which probably also proceeded via a cyclic orthoester. Because formic acid tends to decompose to carbon monoxide and water at high temperature, a still more convenient strategy could be the direct reduction of glycerol with carbon monoxide. Much milder is the desulfuration of thiocarbonates. In this example, a carbohydrate was converted into cyclic thiocarbonate with thiophosgene and then reduced with a mixture of triphenylphosphine and iodine. Let's have a look at some potential side reactions. I've already shown you an example of acid-induced Wagner-Meerwein rearrangement. Acids can also cause pinacol rearrangements, as in this example. In such instances, a thermal dehydration under neutral conditions or a base-mediated elimination may be a better strategy. Sometimes Wagner-Meerwein rearrangements may even occur without any acid. Here, such a rearrangement occurred during the dehydration of a secondary alcohol with the Burgess reagent. Then, as always, substitution can compete with elimination. We already saw some examples of the formation of alkyl chlorides. Here, no alkene, but only a cyclic ether was formed upon heating a triol with catalytic toluene sulfonic acid. Here are some further references which you can also find in the description of this video. Under the Community tab, there's a PDF version of this presentation for subscribers. The next video of this playlist is about the elimination of amines. These are poor leaving groups and therefore often yield the less substituted, thermodynamically less stable Hofmann alkene. See you then.